Okay, so this video is actually going to go over an example for how to use impedances. So now that we have our impedances, we can get our dynamic equations in the frequency domain by treating all elements as resistors. So let's go through a basic example here. We have a voltage source that's powering or sending energy through a resistor, an inductance, and a capacitor all in series with that voltage source. That voltage source is going to be our input in this case. It's something that we're saying that we can control. And we're saying that our output, what we're interested in, is the voltage across that capacitor, just for this example. Let's say it's maybe the voltage of a battery and we want to measure that, or it's something similar to that. So we can rewrite this figure by replacing all those elements, our resistance, our inductance, and our capacitance, by their impedance equivalence, which I described by a block here with a Z in the middle of it. So Z of R would be the impedance for our resistance, Z of L is impedance for our inductance, etc. Our current or voltage source rather is now going to be represented by U of S, and that output that we're concerned about, that's Y of S here. And so what we're going to do is assign a convention to all these elements to figure out what direction their voltages are going in for V1, V2, and V3. And then we're also going to assign a convention for our current here. So let's take this model here and remember or recall what our impedances are for these different elements. Z of R is R, Z of L is LS or SL, and Z of C is 1 over CS. So what we need to do to figure out the relationship between Y and U, if we want to get a transfer function or an equivalent impedance, we first need to solve for I, what that current is for all these elements. So to determine that I, we're going to use the voltage law. We could also get the equivalent impedance by summing the impedances in series, just like resistors here. So our equivalent impedance is just going to be the sum of those three guys all together here. So ZR plus ZL plus ZC, because they're all equivalently resistors right now, that's what our equivalent impedance is. And then we know what the relationship between that voltage there is. That's the voltage of the impedance because they're in parallel. Or you can use Kirchhoff's voltage law as well to figure it out. That voltage is going to be equal to our impedance times our current there. So we can solve for what our current is. It's just going to be 1 over Z equivalent, or the inverse of it, times our voltage, U of S. So now that we have that, let's say Y of S, what we're trying to figure out, that's equal to V3 of S, which is the same thing as if it's like a resistor, it'd be its impedance, ZC, times I here. So let's just plug in these terms here. So I of S is going to be equal to Z equivalent times U of S, or the sum of those three terms, but inverse. And then we can divide by U and shift it over to the other side here. So we can end up with this equation right here, or all the way on the right side here. This is just a simplified version of it. If we multiply the top and the bottom of this equation by CS, we get what our output, our desired output is, that voltage over a capacitor, divided by our voltage from our source here. We get that equivalent transfer function in our model to be 1 over CLS squared plus RCS plus 1. So this method is very useful to very quickly generate some models for linear circuits, circuits with linear elements in them. And that covers our impedance example.